always nice to. Okay. That little thing going to cover up.
I think that's only on your screen.
Oh, okay. Yeah, so it's always nice to get an excuse to come back to Berkeley. Like you said, I did my PhD here about 2 years ago with Matt Pyle and Bernard Sadulay as part of Super CDMS, and then in the later half of my PhD is part of the Tesseract and Spice Herald collaborations. Yeah, the last few years I've been at Los Alamos National Lab in New Mexico in kind of more of the material science type division, continuing working on low mass dark matter, but from a different angle, looking into new and novel types of materials and how they could be useful for detectors, and then also some more traditional qubit-based sensors. So I'll talk about both of those today. Yeah, so I was told this is more of a broad audience, so I'll give kind of a little bit more big picture of what I'm trying to do before getting into the details. So I'm guessing everyone in this room and online has at least heard of dark matter. Very simple terms, of all the energy in the universe, 30% of it can be described as matter. The rest of it, something I won't talk about, but it's what we just call dark energy, and is responsible for the acceleration of the expansion of the universe. So of the matter, or I guess of the total energy, only 4% of it can be described as ordinary matter, which is very well understood and described by what we call the standard model of particle physics, which is all the fundamental building blocks that make up all the matter that we see every day. So of that 30% of the energy budget that describes matter, 85% of it we don't know anything about, and it's called dark matter. This is responsible for the large-scale structure we see in the universe, the galaxy dynamics that we can observe. All of this can be explained by the gravitational signatures of dark matter, but we don't understand how it interacts with the standard model of particle physics. So the entire field of dark matter detection is trying to come up with new theories and tests of some portal between the dark sector and the standard model matter. So keep looking at the wrong screen. We do know a few things about dark matter. Mostly we know how much there is in the entire universe. So we know, I guess you could say the density, but we don't know the mass of the dark matter. It could be a lot of something that's very light, or it could be a little bit of something that's very heavy. And the available mass ranges that it could be here I've shown in this little cartoon, say 40 orders of magnitude. Actually, no, it's way more than 40 orders of magnitude. It could be basically any mass possible. And so there's various theories that say it should be one mass or over the other. And you can kind of constrain it by coming up with a different origin story for how the dark matter came to be. So if you take the Big Bang model and you make some assumptions about how dark matter existed in the early universe, as the universe expanded, that sets kind of limits on how the dark matter would have to interact with ordinary matter, or what mass it would have to be in order to match the observations that we do have of our modern universe. And so the simplest idea for the longest time was there some particle in thermal equilibrium with the early universe. It's kind of creating and annihilating in this equilibrium, and as the universe expands, it sort of freezes and gets stuck at that abundance, and that's what we can measure. And this was known forever as the WIMP, because for the abundance that we saw, it would make the most sense if it interacted through the weak nuclear force, and it had a mass of about a GeV. And so for the past 20 years, that's what the community has been searching for. But thanks in large part to many people at LBL and Berkeley and all over the world, the WIMP parameter space is getting almost entirely ruled out. So for people not used to looking at these kind of plots, we have on the x-axis the dark matter mass, or like the hypothetical mass, and then on the y-axis you have the cross-section of interaction with normal matter, which is basically a probability of how likely it is to interact with the target if it were to be in its presence. And so what these curves mean is that anything above this curve, we've ruled out dark matter can't be. So for, say, a mass of 100 GeV, this sets the strength of interaction has to be smaller than that line there. And this is an outdated plot. It's even more constrained than that. So this simplest model of the WIMP is not, you can never completely rule it out, but the places to look for it are getting pretty slim. So the community has now kind of widened its search quite a bit, and there's many other theories that could explain dark matter. I won't get into any of them really, but the kind of general thing that we're searching for lately is what's called low mass dark matter or light dark matter. And it is masses below a GeV. So kind of in this like electron volt all the way up to GeV range could be called light dark matter. And so in order for these models to make sense in the universe that we observe today, we have to make the model a little bit more complicated and not just have a single dark matter particle, but kind of a rich dark sector. There's a variety of dark matter particles and dark force carriers that interact with the with the standard matter. And so why that's important for this talk is that it allows for the option of dark matter interacting electromagnetically, which with the WIMP, that was not part of the model. Hello. Okay. So yeah, in almost all of particle physics, like accelerator race physics and astronomy, all the particle detectors are based on using electromagnetic interactions. Not all of them, but that's kind of the most common detection technique. And so now having that option for these dark matter detectors opens up a whole host of different possibilities for detection. So in very basic terms, how do we go about looking for dark matter? You can't really create it in a laboratory, but luckily we live in a laboratory full of dark matter. So we're embedded in this halo in the Milky Way. I guess all galaxies are embedded in a dark matter halo, kind of shown in this blue. Obviously, this is not a real picture. And then all the light here would be the visible matter, so everything that makes up the standard model ordinary matter. And, Earth is kind of somewhere in there. And so we're constantly, rotating through this halo of dark matter. We know the density of the dark matter in our halo, and we know the velocity of the dark matter in our halo. And so that means we can kind of quantify the dark matter flux that's just raining down on Earth at all times. And so the idea is you just place a detector in there that should have some hypothetical interaction with that dark matter. The dark matter will go through the detector, and very rarely at some point it should interact, leave some energy in the detector, and that's what we would measure. And then you would get some kind of signal for a given dark matter mass. You'd have some rate, and it would be spread across some energy regime, depending on the detector target. So this is the part that I want to talk about today. How do we make that detector? So there's two different interaction channels that we can look for. So for a WIMP-like dark matter, something that's going to interact with the nucleon of your target material, we just call that nuclear recoil dark matter. You have some dark matter mass with a known velocity from astronomical observations. This collides with your nucleon, displaces it slightly, and scatters off. And you have some recoil energy of that nucleon. So if this was in some solid state system, that would be the vibration of the lattice, and you would measure that as a change in temperature. And so it's proportional to the dark matter mass and the target mass. And so as you search for lower and lower dark matter masses, that energy transfer gets very unfavorable. So shown here is hypothetical dark matter mass, and then the amount of recoil energy that's going to get deposited via this interaction. And this band here is kind of the general spread of all common detector elements, so helium all the way up to lead. So you can see down to dark matter masses of a mega electron volt, which is what we're interested in going below, the amount of energy that's going to be left in your detector is less than a milli-eV. And as you go even lower, we're talking tens of micro EV that we would need detectors sensitive to, which is an incredibly challenging problem to solve. So we have some way to make that a little bit better. And since I said now we can be sensitive to electronic recoils with these lower mass dark matter models, the picture is a little more favorable, but still not great. So this, you could think of this almost identical to making a photon detector. If you have bound atom or bound electrons on an atom, you're exciting them up to the next energy level. Or if you have a solid state system, you have some periodic band structure and you're exciting an electron up to the conduction band, and then you can drift that across and measure it. So the reason that this is more favorable for dark matter is that these are all bound systems, and so the electrons can have potentially an arbitrarily large momentum, meaning you can get a much more favorable energy transfer when you have that two-body collision. And so this dashed line kind of shows the equivalent energy transfer as for those nuclear recoils, but now for inelastic electron recoils. This is just kind of to guide the eye. It would obviously be slightly different depending on the system. But now if we take that same dark matter mass of a mega electron volt, we only need to be sensitive to about an EV of energy. So we're talking 3 to 4 orders of magnitude in improvement. And I guess how good we have to make our detectors. I mean, if we want to go lower, we still need to get down to this milli-eV eventually, which is, I'll talk about ways to do that. But we get a lot more bang for our buck looking at this electronic channel than just the WIMP. So over the last 10 years, this is what people have been doing. There's been a lot of focus on these electronic recoiling models. Many experiments are probing this mega electron to giga electron volt mass range, kind of right in here. And you'll notice on these limit curves that they're improving, they get to a point, and then all of a sudden they completely drop off with a vertical line right here. And the reason for that is pretty simple. All these experiments are using silicon or germanium as their target. And the band gap of silicon and germanium is about 1 electron volt, or I guess it's more like 600 in milli electron volts in germanium. But it's all kind of around that 1 electron volt scale. So really what that means is if your dark matter is trying to excite an electron up to this conduction band, it has to have at least the kinetic energy of that gap to be able to provide it enough energy to go beyond that forbidden region that it's allowed to exist in. And so if your band gap is 1 eV in silicon, you cannot be sensitive to dark matter below a mega electron volt. Really annoying coincidence that dark matter mass of a big M needs a detector with a little m for milli-eV. I can't just say MeV, but apologies if I make it confusing. So this means if we want to get below that 1 mega electron volt in dark matter mass, we need new technology existing. Like you can't improve silicon detectors enough to overcome that fundamental limitation of the band gap if you're looking for this kind of dark matter. And so I've shown that same plot that I showed before, but now overlaid with some kind of existing technologies to kind of guide the eye of what energy ranges these all work in. So, 10 to 1,000 EV detection thresholds are existing things like liquid noble gases, bubble chambers, things that have been in use for quite a while. At the kind of EV to 10 EV range, we're talking ionization detectors using common insulators and semiconductors like diamond, sapphire, silicon, germanium. And see, that's kind of right where it intersects with about the MeV range where we want to go. To get below that, in this like 10 to 1,000 milli-electron volt range, we need things like optical phonon interactions or low bandgap materials, which is what I'll talk about. And then if we want to push even further than that, we need to think about interactions with superconductors, superfluid helium, and things of that nature. So kind of motivated why we want to look for this dark matter below a mega electron volt. And we now know they have very little kinetic energy, which means very little energy is departed in our detector. So to sum that all up, we need detectors with sensitivity to milli-electron volt scale excitations in them. And so we can look for electronic and nuclear recoils. There's reason to look for both. But we need to work on two things for this to happen. So as we saw in silicon, there's just the fundamental limit of the kinematics. We can't excite things smaller than the band gap. So we need new materials to get around that problem. And so once we're sensitive to those low energy dark matter events, we still have the problem of measuring those in the new materials themselves. So we also need to focus on developing new sensors. And so I'll talk about both of those things, starting first with the materials. So the project that I've spent the past couple of years on is a Los Alamos LDRD funded project that we've called the Splender experiment, which somehow stands for the search for particles of light dark matter with narrow gap semiconductors. I can't figure out how we came up with that, but it sticks. And so kind of in simple terms, what we're trying to do with this project is develop novel new materials that have band gaps that are, orders of magnitude smaller than existing commercial grade silicon. So we have a variety of materials that are kind of spanning the range between, order 1 and order 100 milli-electron volt scale band gaps. And what's interesting about these materials is the band gaps are also anisotropic, which means the band structure is different depending on the crystal orientation relative to the thing you're trying to measure. And so the reason that's interesting is as the Earth is orbiting around the sun in this halo of dark matter, the direction that the dark matter will be impinging on the detector will change. And if your response function is different depending on that direction of dark matter, you'll see a modulation signal if there were to be a dark matter signal there. And so most experiments are only able to rule out what dark matter can and can't be. But if you're sensitive to this modulation signal, you could claim a dark matter discovery if you were able to see that modulation. Obviously, that's a very complex analysis and experimental problem, but having that door open is very beneficial with these materials. So we've explored a very big parameter space of different materials and kind of focused in the last year down on these two particular materials. These are known as Zintal phase semiconductors. It's a phase of matter with lanthanide and actinide materials that can result in either incredibly poor conductors or narrow bandgap semiconductors. And so the two that we have are this europium-5, indium-2, antimony-6, and europium, zinc, phosphorus-2. And we use two different growth techniques. A lot of R&D effort has gone into optimizing these growths, and I'm not the one that does the actual growing hands-on. But we use this chemical vapor transport, which you basically crush up all the elements that you want in this crystal, put it in a quartz tube under vacuum, heat up one end, keep the other end cool, and through the magic of thermodynamics, you get a crystal on the other side. Kind of similar process is this flux growth. You put the right ratios of the final material that you want in this quartz tube with some kind of liquid flux, which could just be a metal that melts at a lower point than the rest of your material. So in this case, we just use the natural indium in there as the flux itself. And then you heat it up in a furnace in some controlled pattern, let it cool down in some controlled way. Takes maybe a month of this kind of controlled heating process. And you start to get that these crystals will dissolve in this flux, and then they start to form a nice single crystal that comes out kind of looking like this mess here. But this is exactly the same process as most of you have all done at some point with sugar crystals, where you dissolve sugar in water, put a string in, as it cools, they just grow off the string. It kind of really is that simple. You just do it with a lot more toxic chemicals. And you get this thing that looks like that, and then we hand polish that into something that looks like a nice detector. And so these have measured direct and indirect band gaps kind of in this range that we were hoping for. So direct gap of 60 millielectron volts, and then indirect of 40, and on this one, 300, and then about 10 to 100, depending on the sample. This is early R&D work, so there's obviously a lot of variation sample to sample, so we characterize every single one that we make. So how to actually use these as detectors, we are just making standard ionization detectors, just like you would a normal photon detector. So an important distinction that maybe I didn't clarify earlier, we're using these as intrinsic semiconductors. There's no doping or PN junctions or anything. So it's completely neutral. We put metallized contacts on either side, apply some electric field. You have a photon or you have dark matter come in, create an electron hole pair. The E field drifts them across, and you measure that image charge on the electrode, and then you can integrate that, and that'll tell you how much charge was created. And another thing that makes this project unique over using another kind of artificial low band gap material, for example, like mercury clad telluride, which is what they make night vision goggles out of. Those are heavily doped systems that create an artificial band gap based on kind of like a overabundance of impurity states. The problem is they have a lot of dark count rates because you have all these impurities in there. So when you apply an electric field, it's very easy to thermally excite these impure states, or you get a lot of charge trapping because you don't have very good, or you don't have very long mean free paths of your charge. So they don't make great detectors when you're trying to measure very rare events. So our samples are all single crystal growth. So one detector is one giant pure crystal. I mean, obviously we're still working on impurities. Yeah.
Just for clarity, this is all in cryogenic, right? It's not room temperature.
Yes. Yeah. Sorry. So I'm so used to working cryogenic level. I assume everything is, but yeah. So this is all. A lot of the data we've taken is at 4 Kelvin, but the experiment itself operates at 10 millikelvin. So yeah, that's a downside for maybe the general purpose of these is with a band gap of 10 millikelvin, or of 10 millielectron volts, you need to be at cryogenic temperatures because it's basically a conductor at room temperature. Yeah, so if we have the single crystal synthesis, this allows us to get very pure samples that can be incredibly resistive, orders of magnitude more so than commercial grade samples that we've been able to attain of other types of narrow semiconductors. And just kind of early proof of concept, one of the kind of screening tests that we do of all our materials in addition to resistivity and those types of measurements, is we make sure that they are sensitive to light. So we pulse them with infrared light, and we confirm that they do indeed have a photo response. And we measure this charge collection as a function of the electronic field applied across the crystal. And we see that we're starting to reach this kind of saturated charge collection region. So at low field, what you get is the charges start to drift, but you're either not applying enough field so they recombine and you don't get the full collection, or they get stuck somewhere. If you apply enough field, the charge fully drifts to the electrode and you measure it, and you apply too much field and you'll get that the charge has enough kinetic energy to create another charge, and that's how you make an avalanche detector. So we're not trying to get into that region. We just want to see that we can get to this kind of flat region where we're fully collecting it, but we're not putting too much E field so that we get unnecessary backgrounds. So the way that we read these out in the dark matter experiment is we developed, and this part's important, a material independent cryogenic HEMT-based charge readout. So a HEMT or HEMT, if you're not familiar with working with those, are it's the same as a JFET, just like a field effect transistor. It just works natively at 4 Kelvin or below. And we're not using RF HEMTs like for qubits. These are low frequency, low noise HEMTs optimized for, say, 1 to 1 kilohertz or so. And so the reason this material independent part is important is a lot of dark matter experiments, not a lot, maybe 2 dark matter experiments that are also looking at charge, have been able to achieve resolutions to single electrons. So a single electron created in the material, they can resolve 1 or 2. They can see the difference between all those peaks. The super CDMS HVEV detectors do this indirectly by measuring the phonon signal. As you drift the charge, it interacts with the lattice and creates a heat signal that you can measure. And so the more you drift that charge, the larger the heat signal. And then the Skipper CCDs, which is like a CCD camera that has a way to do multiple reads of each cell. And by doing that, it averages down the thermal noise. And they've been able to get sub-electron resolution. The problem is both of those rely on fairly complex techniques specific to silicon that you cannot just transfer to a material that looks like that no one's even measured the resistance of before. So we can't just use these precision charge measurement techniques on novel materials. And so we wanted to develop an amplifier that would work no matter what kind of material you plugged into it. So it needed to be some kind of relatively contact-free system. And so as our first start for our prototype, we're using a more traditional charge amplifier readout. And in a normal charge amplifier, the energy resolution is determined by your energy gap, which is what we've already minimized with our material. And then you have this noise of the amplifier itself, and then all the capacitance that is seen to ground at the front end of your amplifier. And so the way we minimize all these is the capacitance of the detector itself is determined by material properties and the geometry of the contacts for the electric field. And lucky or unlucky enough, our samples are still small enough that they're just low capacitance. It's about a picofarad. They're right now at about the gram scale, so about that big. The input capacitance is the capacitance of from the gate to the channel of the transistor. And the supplier that we get our HEMTs from it's the same supplier that supplies Super CDMS and Ricochet and all of these other cryogenic experiments. They've developed a low capacitance version of their HEMTs, and since the noise scales with the capacitance, it's also a low noise version of their HEMTs. And so those are about 1.5 picofarads. And then the big one that's really hard for a cryogenic amplifier is the parasitic capacitance. So this whole thing is in a dill fridge. The sample itself needs to run on the mixing chamber. These HEMPs are designed to run at 4 Kelvin. And so the distance between those two stages is, this big. So you have at least a meter of cabling that you have to account for, which I think for like a standard twisted pair, that would be, probably microfarads of capacitance. So when the other things are picofarads, that would completely destroy the signal. So the way around that is we designed a 2-stage amplifier in which we have the first HEMT in the same housing as the detector. There's connected by a fuzz button, which is just like a little tiny ball of copper beryllium, almost look like steel wool. And it's just pressed the detector on one side and then the input pad of the gate of the HEMT on the other side. So it's held together with pressure. And it's an incredibly close connection. So it's very low capacitance from the detector to the HEMT itself. And then it's set up in this voltage buffer kind of configuration called the source follower amp. So all it does is it mirrors the voltage at the input to the output, and it buffers all the upstream capacitance from all the cabling. So by running that HEMT down on the mixing chamber of the fridge, we don't have to worry about any of the cabling capacitance. And we've gotten the entire capacitance down to about like 5 picofarads for the whole capacitance budget. So some kind of unknowns where we didn't know if the HEMTs would even work below 4K because they hadn't been measured before. We were very happy to find out they did. So this actually works. And then in some sense, this would limit the amount of detectors that you could run on your mixing chamber because you would need to have enough cooling power to keep that HEMT cold. And so we've made this prototype and measured it from the measured voltage noise spectrum here. If we integrate that over our signal bandwidth, that noise corresponds to a charge resolution of about 7 electrons, which would be about an order of magnitude better than an existing cryogenic charge amplifier. So we just put a paper out on this on the archive a couple months ago. It should be in the journal soon. So the punchline of all that, where does this get us? So kind of compare the measured properties of these materials with other projections for dark matter experiments. So we make these standard assumptions, 0 background, 100% detection efficiency, and single charge resolution. Obviously not all of those are completely physical, but it's the same assumptions the other people make. So if you want to compare apples to apples, you have to make the same silly assumptions. So this here would be an estimate of what one of our materials would be. All these dashed lines are competing proposed experiments for different readouts and different other materials. Obviously, those are close enough. I can't claim one's better than the other. But up here is the existing parameter space that's been ruled out. We can see many orders of magnitude of new dark matter parameter space we can search. This would be for the case of dark matter scattering. Very similar, this would be the case of absorbing the dark matter. We don't really need to go into the distinctions between the two, other than the fact that in both these scenarios, we see that we're on par with what other people expect from their novel experiments, and we're orders of magnitude better than what's existing. Okay, so that was the materials part. That's how do you get energy into something? And now we want to say, how do we measure the signal that's already been put in these materials? So I focused before on electronic interactions, and now I want to focus a little more on nuclear interactions, or the case of just phonon readout, where a phonon is just the vibration of your lattice. So it's kind of overview of how calorimetry worked for dark matter experiments. So superconducting sensors are incredibly sensitive. For all the arguments I just talked about before, they have a very small band gap, so you could just use them as a dark matter detector themselves. But the problem is they're incredibly small. And so for rare events like dark matter, you need a lot of exposure to something in order to measure it. So you either need a large volume or a lot of time or both. And so a superconductor sensor on itself wouldn't be very good for that. So typically we take some larger substrate, large is relative here, say a few grams of material, pattern it with superconductors, and we measure the phonon signal that gets created in this material. So the heat signal, we measure that with the superconducting sensors on the surface of these. And so usually people use transition edge sensors like TESs or kinetic inductance detectors or NTDs, which I guess isn't a superconductor, but a sensitive thermometer. And they measure the density of the phonon or superconducting quasi-particle population that gets created. And so they're always going to be limited by some kind of Poissonian fluctuation in those densities. And that's what ultimately limits the resolution of those styles of classical detectors. The state-of-the-art detectors are really good. Like we've gotten order 100 millielectron volts by probably people in this room and down the hill. This is a detector I worked on when I was here at Berkeley. But we want to see if we can do better. So a tiny aside to superconducting qubits. So a superconducting qubit, they've been around, I don't know, popular since the 90s. You can think of this as a macroscopic way to simulate an artificial atom. And so you can think of it as it just has unique, discrete, unequal energy levels in the same way that an atom has well-defined orbitals that have unique energy. And so this can be achieved by making an LC oscillator by introducing a nonlinear component to it, which is the Josephson junction. So two superconductors in close contact with a very thin oxide layer creates this nonlinear element that gives you those asymmetric energy levels. And so you have a small superconductor, the island coupled to a bigger one, which is the reservoir, and the energy levels are defined by either the absence or the presence of an excess Cooper pair on the island, where a Cooper pair is the charge carrying unit of a superconductor. It's two electrons or quasi-particles that have paired together to make some new particle that doesn't feel electrical resistance. And so you have these energy levels defined by the number of Cooper pairs that are on that island, but you also have a parity state as well. For every energy level, you can have an excess, like broken Cooper pair, so an excess quasi-particle on one side or the other, so either an odd number or an even number, and that changes your energy level slightly by this phase here. So why is that interesting to what I just talked about? So if we want to make a calorimeter more sensitive than using a transition edge sensor, there's two things that make us want to consider using a qubit. So a lot of qubit groups have noticed over the last few years that if they have a chip with lots of qubits on it and they're tracking the state of all of them, they get that the state can flip in a correlated way on all their qubits, or it's known as like a correlated qubit error, which is consistent with, say, an astronomical event, like a gamma ray or something, hitting the substrate of the detector that is patterned on, creating a bunch of phonons that hit all the qubits at once. And so they've shown that qubits are very sensitive to the things in the substrate they're patterned on, which is great for quantum sensing, terrible for quantum computing, because that's what they're trying to not have happen. And then also, a lot of groups have shown that there's designs of qubits and readout protocols in which you can observe the tunneling event of a single superconducting quasi-particle tunneling across that junction in real time and track how many tunnels have occurred. And so we want to take both those facts and see if we can make a better sensor. And so me and colleagues at Stanford and SLAC and Santa Clara University just put out, well, I guess 2 months ago, put out a design paper on something called the superconducting quasi-particle amplifying transmon, which is a type of qubit, or the squat. So this is based on, like I said, the geometry or the architecture of a transmon, except we've removed the readout resonator. And it uses these quasi-particle trapping techniques I'll talk about next, in the same way that Super CDMS uses them in their detectors to amplify the signal, except where you're replacing the transition-head sensor now with a qubit or just a Josephson junction. And we expect from all our modeling that this should be an achievable path to get to single millielectron volt phonon sensitivity. See, been going a while, try to speed it up here. So this quasi-particle trapping is something that was pioneered by Super CDMS. A lot of that work was done right down the hill at Berkeley. So the idea is if you have two different superconductors of very different superconducting temperatures, they should have a large difference in their superconducting band gap, which is the energy required to break apart that Cooper pair into its constituent quasi-particles. And so the way that this is done in other sensors is to use aluminum as one of the materials, and then you need a lower band gap material for the other. Tungsten is one that's commonly used for the transition and sensor version. But since we need this other one to make a qubit, we have to have a nice oxide layer that we can grow on it. So we've been discussing with collaborators at Argonne to develop Josephson junctions on aluminum manganese alloys, which you can tune very slight amounts of manganese in there to tune the TC to seemingly arbitrary amounts. So this is kind of ongoing R&D. But the idea is if you have some event in here that's a phonon that's bouncing around and it has greater energy than the superconducting gap here, it'll break the quasi-particles apart, excite them to a much higher energy level. They will down convert into phonons and lower energy quasi-particles. And then they just diffuse around this particle on the island here until they reach this overlapping region. And so we have the lower band gap here and the higher band gap here. So in between, there's kind of this, smooth transition of the band gap. When they're in this region, there's a probability that they would just diffuse right back, but there's also a probability that they will down convert into a lower energy state. And once they're in that lower energy state, they don't have enough energy to exist as free quasi-particles in this island region anymore, and they're now confined to this very small region right next to the Josephson junctions. And then at that point, we say they're trapped, and they will tunnel back and forth with some probability until eventually they will recombine or go back into the substrate. So this allows the option to measure them more than once, because every time they tunnel, we get a measurement, and tunnels back, we get another measurement. And so because of this whole process, we have the ability to get efficiencies that are greater than 1. For every stable quasi-particle here, there's a design space here. This is the length of this trap, and this is the length of the island. There's designs where we can get, efficiencies of 10, 15. Even though the tunneling across the Josephson junction is not an efficient process, by trapping them and confining them right by the junction, we can make it an efficient process. And so what will the measurement actually look like? The qubit has a fundamental frequency, and then the charge dispersion is what tells us how different the parity states will be in terms of energy or frequency. Makes more sense for qubits. And so we have some fundamental frequency. As a single quasi-particle tunnels across, we go from, say, an odd state to an even state or vice versa, and we get this frequency switch. And so if we are just measuring what is the resonant frequency as a function of time, we get that this is what an actual measurement would look like. This is just random events. This isn't an actual event. You just get 0 state or 1 state, and it'll oscillate back and forth. And then you would integrate that whole thing, and that would give you the total number of quasi-particles that occurred in that event. So just kind of to wrap it all to the punchline here, happy to talk all the details of this in backup slides, but include them for time here. But the reason that this is worth pursuing is that in a transition edge sensor version of this, you're sensitive to this parameter right here, which is the total energy that got put into the quasi-particle system of your detector. But since the Josephson junction isn't sensitive to that energy, it's sensitive to just the tunneling of the quasi-particles. What we actually get is we measure the total number of quasi-particles. So whatever energy is here, you get an enhancement by the energy of the gap itself. And so to kind of give a scale, for a 1 electron volt event, you would get thousands of quasi-particles that you could potentially measure. And since they've shown that these designs can achieve sensitivity to single quasi-particles, we can say if we have a threshold of a single quasi-particle tunneling, and we can kind of work backwards through all the efficiency factors that we can model quite well, we can say, what does 1 quasi-particle tunneling event equate to in terms of phonons in the substrate? We get that we can easily design a device that's sensitive to single milli-electron volt phonons. And then just similarly, we could think of this as a photon detector, just a photon hitting the sensor itself. This plot shows total number of quasi-particles as a function of energy. So this would be the whole terahertz range here. As long as we're getting more than 1 quasi-particle across the junction, we could measure, say sub terahertz all the way to 10 terahertz with this design. And yes, we've done a first fab run at Slack of these devices. We're doing the entire device out of aluminum first, just to make sure we understand the qubit modeling. Unfortunately, in our first fab run, all the junctions blew, maybe just improper handling. But getting a new fab facility up and running is not easy to begin with, so we didn't have high hopes. But the second round of fab is happening this week, actually. So maybe within the next few weeks, there might be some more interesting results. I'll finally conclude and stop talking. So there's a lot of interesting physics that's happening at this milli-electron volt scale. It's a very difficult regime to probe. We need to make progress on both new materials and sensing technologies. So I've shown you 2 examples of both of those. There's a lot of other projects in that vein we're working on that didn't have time to talk about. But yeah, we're always open to new ideas as well. So if anybody wants to follow up and collaborate, definitely let me know. Stop it there.
Yeah. Thanks. Thanks for the speaker. And I'll start with the questions in the room.
Yeah, a quick one. So you talked about these new materials you're developing, also this new detection technique. With the new material, these indium-based ones, you were talking about reaching, a depletion voltage. I think it was like 150 volts per centimeter, where you sort of reach a nice saturation region with the charge collection efficiency. How does this translate to, if you develop this material appropriately, how large are these detection elements going to be? Are you going to have difficulties biasing it at these temperatures?
Yes, that's a good question. I'll say first, I would love to one day have that problem where I haven't thought about how limiting the size, because right now, they're tiny. So I think that basically say what is the mean free path of these is what would set that. And that we haven't figured out a way to measure in a reliable way. With a lot of trial and error, just kind of putting it in, seeing if it works. So I don't know what that would ultimately equate to. And also, we haven't been able to perform that measurement at 10 millikelvin, that was at 4 Kelvin. So the picture could look a lot better at those cryogenic temperatures. Yeah, it's not really an answer, but
No, it's good.
it's a good question. Yeah.
Hello, so my name is Jan Belecki. I'm working with quantum computers, and one of the issue is entering the data to quantum computer. So now, when I look at your sensor as a photon detector in this mode, how plausible would it be to construct an array of those photon detectors, let's say 20 by 20, which will be 400 pixels, and then couple each sensor with one qubit, and there are devices which have 400 qubits now, in such a way that you could entangle or just set the qubits in the initial state, which depends somehow on the, well, the best would be the energy of the photon, but let's say at the rate of a kilohertz. So that you would just entangle with 1 kilohertz rate the quantum system, and then I could compute on the rest using quantum algorithm, and this will give me the quantum image processing, which has almost no latency, and there is no need to decode the image to the classical bits and then back entangled in the qubits.
So we've talked about something along those lines, but not for that use. But yeah, so right now this is patterned on a wafer or a grid, and they're all individual. But the thought for if this all works how we want it to, the next version of this would be like a 20 by 20 array of these all entangled, and then read them out. Like we were thinking to use it as what we call like a decoherence detector, where they're all entangled, and if any one of them gets knocked off, you get sensitivity. But yeah, I think we're thinking along the same lines, but that use case is very interesting. I think that's very plausible.
Next year?
Yeah.
Really?
I'd like to.
Okay, any other questions in the room? I see raised hand from Zoom, so go ahead.
Oh, hi. Sorry, I'm not turning on my camera. I'm home, but a quick question, which may be misguided on the first type of materials with the low band gap. Are there measurements of the work function of these materials? And my motivation for the question is there a scenario where you can pull out electrons out of the crystal to then do smarter amplification methods?
Yes and no. That is something we've been working on. We haven't figured out a reliable way to measure it, but we've been trying to. It's kind of a phase 2 of this. Once we figure out which materials we can reliably grow and make detectors better, we'll put more effort into the measurement of that.
Okay, thanks.
Yeah.
Okay. Any other questions? If not, well, I have one quick one. So you mentioned in the last slides about the energy threshold, or like you're just calculating the energy scale based on the efficiency. But is there an actual, say, triggering threshold, or like the common detectors right now? So how do you define this? What is a event here?
Like how do we?
Right, like for example, how do you distinguish the signal from the background noise? I suppose there will be some residue quasi-particles just from simulations.
Yeah, so I mean, I guess the simple answer is we understand the background rate as or the dark rate of the devices once they're fabricated and then calibrate them with a, terahertz photon source. From modeling, I guess I can't say anything about unknown backgrounds without measuring them first. This is more of there's no intrinsic reason we couldn't measure this if backgrounds could be controlled. But, yeah.
Okay. Yeah. Thanks. Okay.
Thank you.
Think that's all for today. Thanks, everyone. Stop. Also, questions, right?
Yeah, no, I'm happy to keep chatting.
So I mean, it's the readout is almost like an end cube. Oh, for the qubits, right? Like it's a frequency